Hello and welcome everyone to episode 8 of Talking Shop with Tony Abbey. My name is David Quinn, Chief Marketing Officer at NAFEMS, and I'll be your host for today. This series is a part of our wider community program of online events that we are delighted to be bringing you. You can see more details on the NAFEMS website and more details of Talking Shop on Tony's FE training website. Hopefully you'll find something else of interest as well. This week, Tony's looking at normal modes analysis. We'll kick off as usual with a 30-minute presentation, then open things up to your questions and comments. So without wasting any more time, I'll hand you straight over to Tony.
Thank you very much, David, and welcome everybody to session 8, normal modes and why are they an essential foundation in dynamic response. That's kind of like my thesis for this week. I see a lot of dynamic response analysis in my days of working on the support desk, working with other people, talking to people about and teaching dynamic analysis on our e-learning course. I see a lot of people doing dynamic response analysis without any attempt to investigate the normal modes, which are behind all forms of of dynamic response analysis. So dynamic analysis, people might dive straight into transient dynamic analysis, frequency response analysis, shock response analysis, or random response analysis. These are the main types of the main things you're trying to achieve with, let's say, some form of loading, some sort of loading environment, and maybe leave behind that survey of normal modes. So my thesis is essentially that I think a normal mode survey is essential to support all of these types of analysis. And in fact, I find it's pretty useful in some things like impact analysis. I don't have time to go into that particular idea here, but certainly those of you who've been on the Advanced Dynamics course will know all about that. So I'm saying that if we do response analysis, any kind of dynamic response analysis, we should be doing a normal modes analysis to understand what's going on there. So why the emphasis on normal modes? Well, we're doing linear dynamic response, and the mathematics, if you like, the simulation, the linear dynamic response is made up of a combination of modal responses. And in nature, as long as the displacements are small, then we could argue the same thing. It's going to be a modal combination. So we've got on the dynamics course, we use a gantry signpost holder here, and we do all sorts of things with this poor old gantry. But here I'm hitting it sideways, and I'm doing a transient response analysis. We see the transient response analysis on the right-hand side here, but it's made up of modal content. So here's mode 1 as a normal modes analysis, and I can see that that's a response out of plane, which is what I want. Mode 4 is the next response out of plane. 2 and 3 in between are all in-plane responses, so they're not going to get excited by this particular form of loading. So in this little plot here, what I've done is to show mode 1 and mode 4 separately, and then mode 1 plus mode 4 together. So the kind of the gray line is this wiggly, strange-looking line. Why do we get that kind of response? Why do we get, say, for example, this peak? Well, it's a combination of these different modes. So if I can sort of get into that modal content, if I'm, physically and certainly from the simulation point of view, it is a combination of modes. So why not get in there and understand what these modes are doing? So that's really the idea behind it. And there can be a lot of participating modes. Here I've got mode 1 and 4. If I hit that laterally, then I could have up to these subsets of the modes can get excited in that particular case. On the course, what we do with this sine gantry, we do a seismic analysis, and then it's just really the first mode that gets interesting. And then we actually put it on the old shuttle cargo bay effectively and do a random response analysis and actually launch it into space. And then we go up to about 2000 hertz. So the high modes then play a role. So these contributing modes and understanding them are very, very important. So we want to go and see what they are. So linear dynamic analysis is made up of the combination of these modal responses. If we understand the modal response, then we can investigate the overall response. That's my basic point. If we don't, then we're basically flying blind. If I do, for example, in particular, like a random response analysis, I get some very complicated plots out, like RMS of acceleration throughout the structure. Well, what's that peak doing there? So if we understand the modal response, we can investigate the overall response. What modes drive that peak response? So, for example, in random response analysis, why is that there? And we'll see an example of that coming a little bit later on. Why is the peak response right there? And then if we think about design in the general terms, can we shift the frequencies around? Well, what are the key frequencies? We can usually lower a frequency. Maybe we can increase the frequency by very carefully increasing the stiffness without increasing the mass. Tricky thing to do, but we might be able to do it. Can we reduce the peaks? We know where the peak responses are. We know what modes contribute to that. We know what to attack. So if this particular mode is dominating a response, giving us a peak response, we know that mode. We can look at it and say, well, what physically is driving that mode? Maybe we can redesign, shift that mode around, or reduce it completely. And then if we've got a low response region, curiously, that can be of interest as well. If we're wanting to position, for example, fragile equipment, I want to find part of my structure which is responding to the excitation not very much at all. Then that's a great position to put some equipment or whatever it is we want to put there. So we can check that low response region, understand what modes are driving that, and then look at the sensitivity. If I change the design, am I going to spoil that kind of flat spot there? Sometimes we call that a nodal point. It's not moving very much, or not moving at all in particular mode or group of modes. Or I might want to put some heavy equipment somewhere in the structure, and if I put it at a point which is not basically responding, then it doesn't affect that particular frequency. So I can avoid lowering the frequency. Remember, normal modes, natural frequency is square root k over m. So normally if I put a large mass in, I'm going to be driving the frequencies down. Maybe I can avoid that if that's something I don't want to happen, by very carefully selecting and look at the sensitivity. So there's all these reasons why I want to understand what the drivers are, what the normal modes are. And then somebody is going to be inspecting my dynamic response analysis. So I think this is Inspector Clouseau cartoon. He's kind of looking at my results in here, and I've got, if you look at mode 39, it's kind of wiggling all over the place. Node number 59 has a peak here. And a good question would be, where did that peak come from? Why do we get that peak there at that particular point in time? Why is the other curve so wiggly? And if I just say, well, I don't know, this is just the output from the FE analysis, trust me, I'm an engineer. I've done the analysis. I paid a lot of money for my software, so it must be right. I put a lot of elements into the model. Well, if you don't know, I was quite amazed to see this little cartoon pop up here. It's, I guess it's Mr. Clouseau or Inspector Clouseau giving us the finger there. So you don't know what's driving this. You don't know what's behind it. You're not really giving that reviewer, that checker, the confidence. If you're kind of all over it and saying, well, this is coming from mode 1, mode 4 combination there. This is at this particular point, we're getting like a peak response. Let's say actually we get a peak response about here. And curiously, we get a peak response in this structure right at the elbow there. So if you're all over it and you can describe it and explain what's happening, you've got to bring almost like a little bit of a passion to your explanation of what's happening dynamically. Then that's great. You really begin to convince the checker. Noel, I missed the comment there. So if you could put it into, great to hear from you. If you could put it into the Q&A, that would be great. So we can also have wrong results, or models can be set up very inefficiently. We've talked about design, improving design, understanding, being able to answer questions. But then if we don't have a normal modes background, if we don't investigate, then things actually can go wrong. And I'll show some examples of that. So transient dynamic analysis, frequency response analysis, and random response analysis, I'll show you where how we get things right with transient and random, and where things can go very wrong with frequency response if we don't pick up on these normal modes properly. So I'll give some examples of that. So it's not just a better understanding and sort of philosophically I know more about what's going on. We can make big mistakes if we don't trap these. So a little bit of a background to normal modes. What are normal modes? Well, we can call them natural frequencies, normal modes. it's basically, and in this software that we've got out there, there's all sorts of terms. Some people call it a frequency analysis. Some people call it normal modes analysis, not a natural frequency analysis, an eigenvector analysis. Unfortunately, there's a whole bunch of names for the same thing. What we're trying to do there is to find the resonant frequencies of the structure. That's very specifically what we're trying to do. And both the terms here and all the other terms I mentioned, they talk about the resonance of oscillation. Very specifically, the natural frequency is a frequency typically we want to use hertz or cycles per second, and there's going to be a lot of them. We'll see in a real structure, there's actually an infinite number of resonant frequencies. And then the normal mode is the actual frozen mode shape. Imagine we've got a strobe. We've managed to get a mode oscillating, get a mode vibrating at its resonant frequency. We want to freeze that motion, that shape, and it is a shape. We'll see shortly, there's no scaling on it. We don't actually know the amplitude. That is the shape of it. So that's specifically what we're talking about. We're recovering the natural frequencies and the mode shapes of the structure. There's some other things we recover as well on the way, such as modal effective mass, which are very useful, but this is essentially what we're looking for. Now, as I mentioned, there's infinite resonant frequencies in the structure. I like to talk about, for example, my computer screen here. It's got millions and millions of resonant frequencies. If I put my finger on the top corner, heat up that local region, all those little molecules start oscillating away. We could call that as like a resonant frequency. So, but we're not interested in mode number 5,000,064. It's usually those which are the lower modes we're interested in. Now, they're all there. They're inherent part of the structure. They're sitting there, and some get excited under loading. Others never get excited and just ignore the loading. So, for example, in that gantry I saw, because I'm hitting it laterally, all the vertical modes, dominating modes, just are not interested in that response. So we're creating a list, if you like, or of a survey of all the possible modes that could respond. Some may not. They might be important, they might not be important. Again, that's part of that modal survey, to get in there and understand the distinction between those that look like good, likely candidates, strong players, and those that kind of like this guy here that really just couldn't care less. So FE analysis, the potential frequencies which are infinite, they're reduced to the number of degrees of freedom in a model. But obviously, if we've got 1,000,000 degrees of freedom, I could ask for 1,000,000 modes. That would be a crazy thing to do. Luckily, we're normally only interested in the first few dominant frequency. It would be unusual. So there are some exceptions to this, such as acoustics and so on. But basically, for main structural mechanical type of systems, it's going up to about 50 frequencies that's probably a lot. So it's usually the first few natural frequencies. The energy required to get a significant response out of a structure increases as the frequency increases. So that kind of is naturally a good thing that works for us. If you've got a bridge, for example, 0.5 hertz to 5 hertz is important. Above 20 hertz, it effectively ignores the excitation. So we just drive to a zero response. But we've got to be a little bit careful. Sometimes if we've got a driving input, then sometimes that high frequency content is important to us. So like a racing car, 60,000 RPM, 1,000 hertz, that would then become critical to us. So generally we're thinking these responses tailing off, but we've got to watch out for specific excitation frequencies. So the frequency range, understanding what frequencies are there and what frequencies can be potentially excited, again, all part of the modal survey. What have we got? What are we looking for? What should we consider? Now, theoretical normal modes analysis is a very strange process. In practice, if we want to find out what natural frequencies are in a structure and we go for physical testing, then we've got to either shake that structure, so like a coffee cup holder. This is just a sort of like a diving board. We've got to thump it. We've got to put some form of excitation in to actually see what these frequencies are. And we're not going to pick them all up, because those that are just bored lying around not going to get excited, we won't find them on test. We will find them on a theoretical analysis. So theoretical analysis takes a different route. Instead of actually going into the lab, having to shake or thump something, what we do in the theoretical side is we just say that at resonance, there's a perfect balance between the internal stored energy and the kinetic energy due to motion. There's a kind of flip-flop between these two modes, and the resonant frequencies are where that flip-flop or that interchange of energy is the easiest to occur. So those are special or unique frequencies where we can easily trigger that interchange of energy types. And my apologies to my German friends. A lot of German workers in the earliest 20th century were working in this area, and they label the term eigenfrequencies and eigenvectors. So the frequency is the actual natural frequency, the eigenvector is the mode shape, and eigen very, very roughly means unique or special frequencies. So of all the frequency range we can have from 0 to say 2000 Hertz, our structure has a particular set or subset of frequencies which are these special or unique frequencies. Again, my apologies to my very approximate translation. So in a theoretical solution, we don't need an external excitation. So we can do it without having to define any form of loading. We need to have obviously the constraints in there, but we just look at this approach. And so we can find all the structural frequencies and mode shapes which are inherently there because we're not having to do a specific form of excitation. So it's a very, very powerful kind of technique. The only trouble is that we don't solve the full equation of motion. This would be mass times acceleration, damping times velocity, stiffness times deflection equals our force. This is our equation of motion. These are our typical symbols here. We're saying instead of doing a response analysis, and this could be frequency-based instead of a time-based, we're going to take a shortcut and find something out about the system. So we knock out the damping and we knock out the applied force, and then we've just got an equation in here which is just our balance of the potential energy and the kinetic energy. And we find the roots of these. This is essentially what we're finding is the eigenvalues, if you like, and the eigenvectors, the natural frequencies and mode shapes. So we're taking a shortcut. We're finding this characteristic of the structure without really understanding the response to the structure. We're just finding these fundamental characteristics. Now, the downside of this normal mode analysis, we know the frequencies, we know the mode shapes, but I don't know the scaling of the mode shape. So mode 1 here, mode 4, it's actually mathematically, it's an eigenvector, doesn't have units of displacement. It's just a shape. I gave a kind of dummy presentation to my wife a few years ago, and she didn't really know obviously much of the theory. She's not an engineer. And I mentioned this in my presentation. She said, "I've got a question. Well, what's the point of a normal mode analysis if you don't know what the deflections are?" This isn't my wife. I won't make any further comment on that picture, but she said to me, basically, that doesn't sound very useful. So I replied to her as I normally do, well, trust me, I'm an engineer. Well, what I'm really saying there is that it is still very, very useful. Knowing the frequencies and the mode shapes, very, very useful indeed. Not knowing the amplitude is just something that we deal with as long as we understand these are mode shapes. As soon as we put an excitation in there and we combine these mode shapes together, then we actually get displacements out. We get meaningful amplitudes, displacements, velocities, accelerations, stresses and forces, and so on. So the other problem we have, or the other kind of wrinkle in this, is that we've got two methods for response analysis. We've got a direct method where I've taken out the damping here, but basically we're just solving in terms of x, which is just our physical degrees of freedom, the degrees of freedom we have in our model. So we're solving for, let's say, displacement, velocity, or acceleration through time. The modal method does something a little bit more subtle. It says, let's transform the physical degrees of freedom into these modal coordinates. Now, on the course, I spend quite some time explaining what modal coordinates are, but basically, we know what the mode shapes are, and they're fixed. We get those from the normal modes analysis. So if I scale those through time, they're basically the modal coordinates become the scaling factors through time. I can actually decouple and solve all these equations very nicely, and it makes it very cheap, very efficient. There's all sorts of other advantages of using the modal method. But the key thing for us is the modal method, we've got to use normal modes analysis as part of the workflow. Direct method, I don't even have to touch normal modes analysis, so I can dodge the need to do a normal modes analysis completely from my workflow. So here's just an example of hitting this cantilever beam here, and the modes are scaled through time at 0.02 seconds. This is what the modes are doing. So this is my first mode 1 bending, mode 2 bending, mode 3 bending. This is what they're doing at that instant in time. I combine them together and I get back to the physical response. The physical response, just looking at the individual, I think there's 12 degrees of freedom here. Here there are 3 modes which I'm combining together. So we can do it either way. There are big pros and cons in there. That's a big discussion about what's going on there. If you use a direct method, as I mentioned, you don't need to use a normal modes analysis. Now that could be seen as an advantage. I just want to go straight to direct method, physical degrees of freedom, and often I will do that because of the pros and cons, the pros there. But if I only do that, there's a big trap waiting, because no modal survey is possible if I do a direct method. I've really got to take the time to say, direct method doesn't give me modal results. I'm going to do a modal survey as a separate kind of part of the workflow now. It's not inherent in producing the response analysis. It's a choice I make now to say, as well as doing my direct, let's say, random response analysis, I'm also going to do an investigative normal modes analysis as almost like a side step now, rather than being part of the workflow. So that's leads people down that path, and that's why I call it like this little bit. I'm going to call it a bear trap. There seems to be some sort of ant trap in there. I don't know quite how I got that up there. So let's look at a transient analysis example of how normal modes can be useful. I've done my modal survey. Here's the first 5 modes, and it's some sort of tray cantilevered off here. Here are the first 5 modes. We get a torsional mode, a bending mode, a sort of extensional mode because there's a large payload mass in here, and a couple of local wall modes. I've decided that's high enough. I don't need to go up further up in here. So already the modal survey has given me a sense of what frequencies are important. So if I do a frequency response analysis or transient analysis, what modes become important. Now for the transient analysis, I can use that information. I want to apply an excitation through here, so it's going to be a little impulse coming through here. And what I want to do is to excite all the modes in that range that I'm interested in. I want to estimate, for a transient analysis, I need to know the time step size, and I want to know the duration of the analysis, or the number of time steps. And I don't want to guess at these. I see a lot of people guessing at these, but there's absolutely no reason to do that if we know the natural frequencies. And this is the way we approach it. We say the time step size, the highest frequency of interest I've said is going to be 1804 Hertz. Turn that upside down into a time period, 5.5 e to the minus 4 seconds, and then basically that would give me one full oscillation. I want a minimum of 10 time steps to describe that oscillation. Remember, this is the highest frequency of interest. So I divide that by 10, I get 5.5 e to the minus 5. I round down because we like nice numbers if we're going to be plotting and if we're going to be comparing plots and so on. So that will give me 5 e to the minus 5 seconds. So there's very simple logic there. If I can capture that fidelity of that highest frequency of interest, by definition, I've got the fidelity of the lower frequencies as well. I also need to check the fidelity of the loading input. Is this number of time steps over this input sufficient to describe the loading? In this particular case it is, but that's just something else we'd have to watch out. So there, the highest frequency of interest is dictating the size of the time step. And now the duration of the analysis, I don't want to waste time running it on for too long. I don't want to cut the analysis off too short because I'm not convinced that maybe there might be a bigger overswing later on. So the logic here is that the impulse is on for about 0.01 seconds. That's my transitory period. I want the response after that to settle down, the steady state oscillation to settle down with a decay rate based on the damping level. So I want to see that, again, where is that early swing? Now, that overswing or that highest response. Now I use the lowest frequency, 108.4. And I typically use 4 cycles of response with damping that allows that decay to occur. And I can check to make sure I don't overswing somewhere during those four cycles. So again, the lowest frequency of interest, turn it upside down, gives me a time period. I want 4 of those. So 4 of those gives me this time period. Add that to my loading time period, and then my duration estimate is this value, 0.0469 seconds. I've got a time step of 5e to the minus 5. That gives me 938. Well, again, awkward numbers. That's rounded up to 950. You could call it 1,000. And now I've got my time step size and my number of time steps. And this is the result. Here's my 4 overswings. I can see clearly it's damping out. There aren't actually any surprises here. Sometimes what happens, though, is because of the phasing, if it's a more complex structure, we suddenly get a kick coming in here, and that might be, say, this response to this point here could be bigger than the initial response. That's what we call like an overswing due to the phasing effects. I want to demonstrate to everybody that there's no surprises down in here. In this particular case, the peak response is up in here. So that's the idea of that. So there's a transient described very nicely in terms of the time step and the number of time steps. Very easy thing to apply if we know what these frequencies are. So coming on to now a frequency response analysis. Now I want to drive this structure across like a sine sweep. So I want to put in a harmonic oscillation in there of unity running through in here across that frequency range. So basically up to 2200 hertz, it's like putting something on, or putting like a stinger in here, exciting and increasing the frequency of driving that. Now the first time through, I'm going to use what I call a blind strategy. If I haven't done a modal survey, I'm just going to say, let's use, go from 10 hertz to 2200 hertz, which covers the span. 50 hertz sounds pretty fine. So let's try that and see what happens. So if we run at that, and then we look at the frequency response, these are the modes again, and this is my frequency response curve. This is at the payload mass, which is the center point there. You can see it's a horrible sharp point in here. There's no smooth curves. Mode 2 is missed completely. I just don't get anything around there because I haven't got any points where I'm doing the calculation. Every other mode misses its resonant frequency. So it's basically a very, very poor representation between the resonances. So we're just not getting any degree of accuracy whatsoever in that calculation. So we need to have a different strategy, and it's going to be based on the normal modes, because we've got to basically, my motto is hit the peaks, which are the resonances, fill in the valleys. Let's have a good distribution of data in the valleys. So what I do there is I say, well, let's say each mode, we've got to have a point right there, and then a spread 1%, 2%, 5% around them. You could use a half bandwidth type approach, but this is often the approach I take here. Then I want 10 results between the resonances. So then that achieves the target, hitting the peaks, fill in the valleys. Now, this has huge implications for random response analysis, because we take the area, essentially, of a frequency response curve, and we square that and we multiply it by the input PSD. So if you've got, let's go back to that one, if you've got that kind of curve, you're going to have a terrible PSD response. Your random response analysis is going to be really, really bad. So big implications for random response. Now, if we use a modal frequency response, the workflows these days, they can pick up the normal modes automatically. I can remember when we first introduced that, and if anybody ever meets me, we can have a beer and I can talk about what happened when we automatically gave people the right answers, if you like. Direct frequency response, you've got to go and find that normal modes data, or there's got to be a workflow to say, somewhere I've got to run the resonant frequencies normal modes analysis anyway to know what these frequencies are, so I can put them in my data table and build up a data table of where I'm going to do the response calculations. So modal, it tends to be natural. It's just kind of synergistic. Frequency response, you've got to do that normal modes anyway. And again, that sometimes I find people just, again, guessing, as I talked about with that very bad strategy, which is just this strategy here, and it really isn't good enough in frequency response analysis. We've got to hit those peaks and fill in the valleys. PSD input, a random response analysis example as well. What I'm doing here is I've got a plate, just a very simple plate, so a very simple structure. I'm oscillating up and down, so shaking this is, say, a massive piece of machinery, oscillating up and down. I've got a piece of electronic equipment which is sitting here at, let's say, call it point number 1. I want to check to see what the RMS acceleration is at that particular point. Well, in this particular case, my dominant modes are mode 1 and mode 3. Mode 2 is a torsion mode, and that's not doesn't get excited, so it's first bending and second bending these particular resonant frequencies. Now, I've done a modal survey. I know what those resonant frequencies are. In the PSD analysis, the random response analysis, I've got an input PSD, I've got a frequency response. The frequency response will tell me the deterministic frequency response at that point from the loading, so it's really a representation of the transmission through the structure here. The structure acts as like a filter and gives me the responses here. I then multiply that by the input PSD, which gives me the randomness of the signal going in. So normally we're used to plotting an output RMS. So the calculation at that particular point is I've got an RMS of 6.31 G. That's what's going in. I can't remember what the RMS of the input signal is now, but we've got 6.31 G. Normally we'd multiply by 3, so just under 20 G would be the worst case scenario for acceleration at that point. We compare that to the fragility of the equipment. But rather than just looking at that number, this is the output PSD. So this is the input driving PSD in blue. That's the output PSD at that point number 1. What I can see is the influence of the two modes. And I can see that mode 1 is in what we call the roll-off period, the roll-off region of this, so there's not much power coming through there. So that's useful. Mode 3 is slap in the plateau region, so that's getting the highest response. But if we just looked at the frequency response, the mode 1 would be a bigger contribution, but it's being rolled off a fair bit in there. So we could say, well, in our design, let's try and shift mode 3 to get that in the roll-off period, or let's try and lower mode 1 further. But I can see the modal contribution, or the mode-by-mode contribution, to that RMS value. If I take the area underneath that red curve, that's my mean square, take the square root of it, that's my RMS. But I can see where it's coming from, which can be very, very useful indeed. So it's giving me that insight that I'm really, really looking for there. Now this is the result of the full plate. This is the 1-point calculation in here. Now in the course which I've taken this from, we actually go through and explain how we can do that. And we actually do a little spreadsheet shortcut to say just point 1. I can actually do the graph and then do the RMS by hand, as it were, or at least by Excel spreadsheet. Here's an FEA result which just calculates all the RMSs automatically, the root mean square accelerations. So I can see that that point there is not the worst point. The worst point is in the middle here, but it's a bad point to put a piece of equipment. There's an interesting region right in here where it actually would be a very good position to put a piece of equipment. We've got the RMS down to about 1.1, so that would be great to do that. So we also, as well as the RMS, we have an apparent frequency, which is essentially like the average frequency. So here, the apparent frequency is like the smeared average of this and this, so the apparent frequency is somewhere around about 105 hertz, I think, in that particular case. So here, what we're finding is the apparent frequency is down at this point here is lower. It's actually down to very close to that first resonant frequency, which is giving us a little bit of a clue there. So if we look to see what's actually happening there, this is the output PSD in the green at that particular point. So node 749 is that interesting position where we could put a piece of equipment. What's happening is that mode 2, mode 3, the second bending mode, is actually getting snubbed out there because it's a nodal line. We've actually got mode 3, I should say, in this particular case, the second bending mode, is actually at that particular station. There's no response, so it's basically bending underneath there, or deflecting down, then deflecting up, and going through a zero line through here for that mode 3, the second bending mode. So it all ties up. There's no interest in mode 3 there. It's all dominated by mode 1. We can see the apparent frequency doing that, and the RMS is down to 2. So this type of investigation, why are we getting that low RMS value in that region? Again, very powerful. If if I know nothing about the normal modes, then basically I'm kind of flying blind there. So hopefully some examples to sort of show why I would want to do these normal modes analysis as a modal survey, essentially, as an essential part of any kind of frequency response. I've got lots of other examples. I could talk more about that, but I'm kind of running out of time, so I better wrap it up quickly now. And basically, in my view, normal modes analysis is critical. We should be carrying out a full modal survey. We want to understand the frequencies and the mode shapes. We want to use these to plan the response analysis, like we did with the frequency response, and the time steps and the duration. But we also want to use these to verify and understand the response, understand what's going on there. So that's the thesis. I hope I've defended it okay. And I think at that point, thanks very much for watching. I'll curate the video, tidy it up, and the questions which are going to follow, we'll put all those up, put them on our websites. Next session, June the 26th, we're going to be looking at stress concentrations and stress singularities. Do we care about them? Well, yes, we do. And here's a shameless little plug. The next dynamics e-learning, which I've taken some sections out of, if you're interested in that, that starts on the 2nd of July. And here's a link to that. If you also go to the NAFEMS website, look for e-learning, then you'll find the registration there. This is a shortcut I've done to that same registration site. So I will hand over to David now, again, the same voice of David Quinn, to wrap up and take us into the Q&A.
A compliment, Tony. That's always nice to have on our Friday. Thanks very much for that. As usual, we do have a ton of questions coming in on the right-hand side there, based on the presentation. Can you see those okay?
Noel Bill says slide 5-6-ish. I see used an amount of damping. Is that advised, or I should initially use no damping, as damping is difficult to assess? I normally would put some form of damping in. If we're going to do a frequency response analysis, then it's important we put some level of damping in. If we want to be very conservative, we would say put 2% damping in. That would be my usual kind of typical lower bound. If I put zero damping in a frequency response analysis, I get basically crazy results at the resonance points, and then that laps over to the other points. So I tend to want to put in a small conservative value like 2%. And then for transient, again, I would tend to put in a level of damping in there, say typically 2%. It just stops at resonance getting very, very strange results. That's the reason why I do that. The reason why I was asking for mode 39, I see the participating sheet peak shifting. I could miss that when using no damping. The frequencies in a linear dynamic analysis, the frequencies won't change as a result of changing the damping level. One of the things we say is that we avoid the damping dependent part of the response, and that's essentially we assume that the damping is just going to remain linear, so it won't actually shift the frequencies around there. So again, perhaps I'll show a couple of equations there on when I create the QA. Peter makes the mark, if you use normal modes basis for a coupled structural acoustic, you could easily go up to 5,000 hertz. That's right, Peter. That's why I was very careful to exclude acoustic from my discussion. Acoustic is a nasty type of dynamic analysis in general response analysis, and we can have up to 5,000 hertz, huge number of frequencies, very, very close coupled frequencies, very, very difficult to figure out what's going on. So I think a modal survey might be giving you way too much data. So there's a very, very special kind of analysis there. Daniel asked a question, can all types of modes, first mode, torsional flapping and so on, be detected if excited axially, for example? No, that's really the point. If we do a normal modes analysis, then we're saying there's no form of excitation. We're just doing a survey of every potential mode. If we do a response analysis, such as my gantry here we're seeing in this particular screen, I'm only going to excite those modes which get interested in that particular response, which are going to be the outer plane modes in here. Notice I've jumped from mode, I think the previous slide, we jumped from mode in here, we jumped from mode 1 to mode 4. Mode 2 and mode 3 are just not interested in what we're doing. So excitation, specific loading, is only going to excite a certain subset. Normal modes analysis basically just goes through and will give us all of the potential modes, which is the good part of the survey. Xavier says for very high frequency excitation, piezo exciter application, do you think modal analysis using common FEA codes is relevant? Any comments regarding mesh size versus wavelength? Yeah, there are other methods, and this kind of ties up with the acoustic method. If we've got very high frequency content, very closely spaced modes, then I'm not actually, I'll never use these other methods, but there's a modal energy method. I've forgotten the exact term now. Again, I'll try and put that up in the curated answers. You'd go to an energy-based solution, and I've never used this, but you're basically saying we not have the mesh dependency and all of the issues associated with trying to do this with FEA. If you've got something like a car roof, you're looking at very high frequency acoustic response, you've probably got thousands of modes, and to pick up the subtlety of those mode shapes, you normally need about 4 or 5 elements per wavelength to capture the mode shape. And if it's such a small wavelength, then the mesh just gets ridiculous. So yes, there are energy methods which kind of, thank you, Vivek, statistical energy analysis method, that's it, perfect. So that's what I'm talking about. Those are alternative methods. I don't have any experience there, but I know my colleagues and friends in the automotive industry, for example, certainly are using that kind of approach. Noel says on slide 13, does modal mass, participating mass, give an indication for the scaling of the modes? Yes, if we've got base-driven excitation, so if this gantry I'm looking at now is actually driven through the base, then there's a direct relationship between the modal effective mass and let's say the frequency response analysis. Sometimes we even call it a poor man's frequency response analysis. If we've got a general excitation, external excitation like this, we're hitting something rather than driving through the base, there isn't a direct relationship between the modal effective mass, but we can still say the modal effective mass is telling us what the big players are. So modal effective mass is very, very important for, I haven't touched on that, but it's a good point. It's a very important part of the modal survey. That probably be another whole other talk, how to use the modal effective mass. We go very heavily into that on the course. Chip makes the point, when I'm mentoring younger simulation engineers, modeling complicated systems with multi-components and interactions, I require them to run a normal modes analysis to shake down their model, a very efficient way to understand the system model. It is. I completely agree with you there, Chip. I've been focusing on dynamic analysis and dynamic response and saying this is important to understand what's going on. But in fact, any structure, even if we're going to do a static analysis, I use a normal modes analysis as a shakedown to make sure I understand that structure. If I'm dealing with, let's say, a complicated mesh, I'm using linear bonded interfaces to make sure it's all hanging together properly. There's really no better way than to run a normal modes analysis to see that the structure's hanging together properly. And again, it can give you some insight. As a designer, you can see where the stiff load paths are, the more flexible load paths are by doing a normal modes analysis. So I like the idea of extending this idea into other solution types. Andre asked the question, is there a way to handle in a modal analysis a nonlinear contact behavior? I mean a face-to-face contact where we want to allow one face to detach from another. I've not done very much work in that area myself, but there are techniques to handle it. One simple way is to maybe run a transient analysis and see the adjusted frequencies, because what's going to happen is we're going to be truncating the time period because it's going to be hitting against the stops. And you can do approximate approximation methods to say, well, if we clip the motion, if you like, we're reducing the time period, we can make an estimate of what the equivalent resonant frequencies are. There are other more sophisticated ways of doing that, but I haven't actually handled them myself. Ed says, can you explain why we should use residual modes in an analysis? This is almost becoming the e-learning dynamics course, but sure, a residual mode is, we use that because one of the problems with doing response analysis using a modal method is we may truncate, like particularly a transient analysis, we may truncate the higher mode shapes. And if we don't have a representation of the higher mode shapes, we're missing some of the physics. The residual mode is basically saying, well, if we apply the transient analysis with a loading input, if we take a static deflection shape of that loading input, we can then take off or subtract all our modal shapes from that, and the bit that's left over, we can say that's associated with a higher frequency content. And that generally works very well. So you create this residual or artificial mode, which is the bit that's left over from the static distribution from the load that you're applied, after you've taken off all the modal contributions. You orthogonalize it and so on, fit it in, and so that fake or that residual mode plays a role in representing the higher mode shapes. Peter, it might be interesting to Peter makes the point, it might be interesting to remark that structures with symmetry, you get multiple modes at the same frequency. Whoa, symmetry is a big question. I see what you mean. So yes, if we've got something like let's say a circular rod or a beam, circular cross section, we actually get two modes which are actually orthogonal to each other, but they have the same frequency. That's what we call repeated modes. What a repeated mode is really telling you is that we could be exciting that we could have a response in the y direction, or let's say the z direction of our beam, and we don't know which one it's going to. We don't know that particular direction. So what the mathematics is showing us is two repeated routes to say it's characteristically lateral and vertical outer plane response. You pick whatever direction you want to do if you're just going to be doing a normal modes analysis. So basically, it doesn't know what direction to do, so it kind of gives you those repeated routes. It's a very interesting kind of topic there. Abhi asks, what's the difference between direct and modal response? Essentially, as I showed in the slide, let's get back to that slide. This was the quick 2-minute overview of something that I normally spend about an hour or so describing what's happening. The equation for the direct response is just the equation of motion. So x is our physical degree of freedom. It's our direct method. We're solving directly for the unknowns, which are fundamentally displacements, and then velocities, and then accelerations with our equation of motion. Rather than doing that in a modal method, we've said we've already got the mode shapes. So phi is the collection of mode shapes. It's a set of columns of mode shapes. So if this is 3 modes in here, it's 3 column vectors which describe those 3 mode shapes. And Q would be 3 values of scaling through time. So we've said that a response can be thought of as a combination of these modes through time. So what this little expression is doing in here, it looks nasty, but all it's doing is ready to say the response can be thought of combining these modes as the mode shape remains fixed, but we're scaling it through time. So any instant of time, we combine them together. And then we can solve in these modal coordinates, and then we can back substitute to get back to the physical coordinates. But the essence of the modal coordinates is this. This is the physical coordinate right in here, and this is our modal coordinates. So the physical coordinates, just to say x, so these are all the deflections, or so these are deflections at that particular time in x, but they're made up of these modal contributions at time x. So here's mode 1, mode 2, mode 3. The beauty of this is it's cheaper and more efficient to solve the individual modes, and then we combine them together. Also, I can do things such as filtering out modes, and I can play games with these modes. So I tend to use both. when I'm evolving the design, I'm checking the responses, working with the analysis. I use modal a lot to get an understanding. This is a modal transient, having already done my normal mode survey. And at the end, I usually do finish it off with checking it with a direct transient, just to make sure I haven't missed high frequency content and other things might have come in there. So it's the two approaches essentially in there. Stefan says there's always an issue with damping coefficients. Do you have solid values of Rayleigh damping coefficients for different materials? I don't actually like Rayleigh damping because we are defining basic quadratic variation of damping as a function of frequency. Well, it's not quite a quadratic. We can think of it like let's say a polynomial function. We're describing as a damping as a function of frequency, dependent on the coefficients we use to describe that equation. If we make mistakes in those coefficients, then our damping curve can be all over the place. So if I have Rayleigh damping coefficients alpha and beta, I normally like to go to an Excel spreadsheet, plot them out to see what that damping looks like, and then see where it intersects my main frequencies of interest. I prefer to use either structural damping or to use modal damping. Damping is dependent on materials to some extent, but it's also dependent on the structural form. For example, for fabrications, there might be higher damping level than for an integrally machined component. So it is partially dependent on the material, but it's more dependent overall on the environment that the structure is sitting in. I generally talk about on the course damping levels running from very, very light damping, say 1%, 2% for something which is an integrally machined type of structure, all the way up to say maybe 10% damping. If we've got something like a composite material where the material is playing a role, the inherent damping in the composite, and there's a lot of fabrication going on. So the amount of fabrication and to some extent the material plays a role. Anything above 10%, then we're getting into damped, we're getting into the nonlinear regime where basically the damping is starting to shift the frequencies around, going back to Noel's question. So we talk about their damped natural frequencies as opposed to undamped natural frequencies, and then we get a shift of frequencies at that point. Linear dynamic analysis assumes that we don't get that shift. We simplify the equations. So anything above 10%, and certainly if we go say to 20%, this is all percentage critical damping, we should really be running a nonlinear analysis. Again, maybe another talk on damping would be a good talk, or come along to the dynamics course. Marina says, to get the overall modal behavior of an assembly, is it enough to do a modal analysis of the single components, or do I have to analyze the whole system? How do I do that best? Really, you've got to put the assembly together, and then it's the dynamic interaction between the components is going to give you the overall assembly resonant frequencies. Another approach, which is sometimes taken, for example, in suspension systems in the automotive industry, is to say, from experience, we want to make every component to have resonant frequencies, let's say, above 300 hertz. And this can only come from experience. If I make sure each of my components has a resonant frequency above 300 hertz, when I bring them together, I've got some feel that I'm going to have the higher frequency content I want. I'm going to keep those frequencies up. If I don't want the whole system frequency to go below, say, 60 hertz, maybe if the components individually are, say, 300 hertz, that will won't always guarantee, but there's a very good chance then that my system frequency will meet my targets. So that's one way of doing it, to say, and it can only be based on experience or trial and error, what would be a good value to use as a target frequency for my components. Otherwise, we've got to put everything together and run it together. Peter says the concept of modal damping, which damping is defined through a combination of modal stiffness and modal damping. Yes, I like that approach, and I would recommend that. Peter's saying typically use 2 to 3%. Yeah, very often if we don't know the level of damping, I might run with 1%, 2%, and then maybe 5%, just to look at the variation in response. And the key thing is that the lower damping is always more conservative. So if you're not sure, you always go lower. I've seen people just put like 5% in because it seems like a good number. That's dangerous because it's obviously suppressing the response. The response level is totally dependent on the level of damping we put in. If we're near resonance, it becomes quite critical. So if you're not sure, 2% is probably a good lower bound, and 1% might be an even more conservative lower bound. Can I know the damping percentage for structural damping during durability loads extraction? Again, it's something that the damping, we can only really nail it down if we've got some test evidence. So unfortunately, we've got to go for test to give us a good value for damping or previous experience and so on. Peter makes a comment, in principle, you could use 6 to 8 elements per wavelength for wave problems. Yeah, that's the kind of number that I like to use. So take the highest frequency of interest, not the highest frequency, the most complex, busiest looking mode shape, basically the shortest wavelength mode shape, and then try and make my mesh to have 6 to 8 elements for that. So you can see if I've got a very high frequency content with very, very complex mode shapes, very short wavelengths, that's really punishing the mesh fidelity there. I think we'll stop with one more question now. There's a bunch of others, so I apologize for skipping these. Stefan makes a comment, in order to save computational time, I tend to use modal superposition. Contact between components is frozen in this type of analysis. Could that be a problem when solving systems where you have some sliding between contact surfaces? Yeah, any of the modal methods, by definition, are going to be linear, which means you've got to bond or glue the contact together. And that's often a very useful first pass, and I often use that kind of approach. Even if you used a direct method, it's still largely a linear type method, although I believe there are some techniques that allow you to kind of slip in a little, maybe some gapping, but I'm not experienced with that myself. The only way we can really understand gapping or contact between components making and breaking is to use a nonlinear transient. So that is by definition a direct method. It's a good idea to shake down a complex assembly just to bond everything together, look to see what you've got, and then you can start to use engineering judgment call on, well, is that really a reasonable kind of approach to use in there? What I've done then is to say where I think there's some softening of the connection between the components, put in linear springs, which would to some extent would represent the allow you to have that change in frequency I talked about between something which is let's say something oscillating in a slot. If we don't have the edges of the slot, it's just a free oscillation. We put the slot in there, we're constraining that component to move within that slot. We're usually driving the frequency up. So if we have some estimate of that, we can actually put in local springs differences to actually drive those frequencies up. So that would be part of the process I would go through if I wanted to avoid more complex nonlinear transient analysis. In the sliding contact can be, Chip makes a comment, sliding contact can be handled with linear constraint equations which connect 2 degrees of freedom. Yes, that's a good point. If anything's sliding over each other, we can either have that as a contact relationship, which is linear, or we can just say it's just simply a linear dependence. So sliding surfaces can be set up as constraint equations, as long as the relative motion is not too big. So that's, again, a very good point there. So I think we'll stop it there. I think my general thesis seemed to be accepted because we just had a lot of questions which are diving into other aspects of dynamic analysis. And it's certainly given me a bit of a hint. Maybe we need to kind of revisit dynamic analysis on some other of these talking shops. So I think with that, I will wrap up now and hand over to David to close the show for us. And I'll just move you back to our nice marketing slides at the end here, David.
Fantastic. Thanks very much, Tony. And thank you to everyone for your questions today. It's always great to get some interaction on these sessions. As Tony says, he'll be spending some time now, probably over the weekend. Poor you, Tony, putting together the curated Q&A. And we'll get the videos onto both the NAFEMS website and Tony's FE training website. You can go back and have a look and look at the questions, the answers to the questions that we haven't been able to cover today. So with that, we hope that we will see you on the 2nd of July, on the 26th of June. I'm reading the wrong part of the slide, Tony. 26th of June for the next talking shop on stress concentrations and stress singularities. We've worked out already we do care. Tony's going to discuss why. So thank you everyone for joining. We hope to see you very soon at another NAFEMS event. Have a good weekend and take care. Goodbye for now.
Bye, everybody.